to be here. With Rogerio, we have been collaborating for a long time on particle physics until he moved to cosmology and expanded in other dimensions.
Then you moved to cosmology.
Yes. So this is, well, as it was supposed to be informal, the talk is going to be a little bit informal, but still I have prepared something. Well, this is a view of Sao Paulo. This is the Pinacoteca, I think, right? This is the Sala San Paulo, one of large auditorium.
I thought it was Valparaíso.
No. This is Sao Paulo, and this is it's a kind of street in Cantareira. Look at that. So anyway, this is a collaboration with some colleagues, Ivan Schmidt, Sergei Kovalenko, and Adam Smetana. The idea here is to try to build a way of having low-scale seesaw. I will say what low-scale seesaw for neutrino masses is in a dynamical way. So to say, by the interaction of some heavy neutral leptons that somehow with an extra interaction they become strong, so they form bound states and then they condensate, and then you have some kind of dynamical description of this lepton number violating terms that cause the masses of neutrinos. And one can speculate that this could also lead to the origin of leptogenesis, and some of the bound states, scalars, could be candidates for dark matter, and so forth and so on. And so if one uses only the fields of the standard model, one can build a dimension 5 operator for the mass of the neutrinos. Basically, you need just to use two left-handed lepton doublets that you combine each one of them with the Higgs, and so you form a term of like something like that, right? So this is dimension 5, so you need some mass scale here where this operator becomes effective. And actually, in any kind of model, you can reduce at low energies to something like that. But the point is to kind of open this operator and see what's inside as a more fundamental level. So there are many possibilities. The simplest ones are called Seesaw, which essentially you include an extra field, which is where's the pointer here? There. A right-handed neutrino, which is in the standard model is sterile, so it has no interactions. And you build the Yukawa term, which is, well, it's not a very happy term here because the Yukawa, to reproduce the masses of the neutrinos, has to be extremely small, 10 to the minus 12 or something. And worse than that is that the neutrino, since it's a sterile field, you can actually also have a Majorana term with some fundamental mass there. There's no reason to exclude that, except if you want to, impose lepton number conservation, because this term violates lepton number by 2 units. So if you keep this framework now, when you have the breaking of electroweak symmetry, you end up with two terms for the masses of neutrinos that combine into this mass matrix that you can diagonalize, and you end up with two Majorana neutrinos, one that is of heavy, of the mass of the order of this large M, and the other one which is lighter, which is the order of this other M, small m, square over large M. And this M small here is coming from, as we say, from this Yukawa here. But now this mass M can be of the order, for example, if you take the Yukawa over the 1, then m is of the order of the top mass. And then you need a large m, 10 to the 15 GeV, to reproduce the neutrino masses, which will be like cut scale. And the mixing of the light, of the light neutrinos with the heavy ones come to order 10 to the minus 8, so rather suppressed. So the heavy field decouples. And if you want to be a bit, not so extreme, but you accept that this m could be the electron mass, then m is not so large, well, but it's still 100 TeV, and this rate, I think they're the way around. But anyway, it's also very suppressed, so the heavy field will decouple. And yeah, I think they're the other way around. So now there are other scenarios of, this is a Seesaw, because Seesaw is, this toy for kids. So as one mass goes up, the other one goes down. Seesaw. And then there are some other constructions called, well, this construction has no name actually, but later on was called low-scale Seesaw. From other theories, you can end up with the inspiration of having more fields. Here you have two extra neutrinos. You have one that I keep the name nu R, and another one is called SR. They are both neutral leptons. And you can build this like a mixed term with also a mass with a fundamental mass here. But now, since you don't have a new term, but S new term, you can assign to this one lepton number opposite to nu, and this term conserves lepton number. And here, of course, you conserve lepton number. So in this matrix here that you have now, in one generation, you have a 3x3 matrix. You have lepton number conservation still. And you have a heavy neutrino of that mass order. But the problem is that your lightest neutrino is massless, because lepton number is conserved. So it doesn't really help you very much if you want to explain the small neutrino masses, because it's still massless. So then the idea is to conceive something that generates some small terms here that will create a small neutrino mass. Yes?
Why don't you have the UR square
Here?
term?
Well, you can. You can have that. If you do that, you will have a term here in the middle, and that violates lepton number. And you're essentially going back to the other previous Seesaw model. You could, yeah. If you realize, if you add a term like that, you will have a M term here, and you have this matrix, which is exactly what you had before, except for the other fields.
Do you assume that this symmetry, lepton number symmetry, to be respected
in this case? In this case, you're assuming this is respected, but of course it's not good, because if you assume that, the mass of the light mode is 0. So we have to break this symmetry now. But the point is now you break the symmetry softly. And so this is what's called a low seesaw, low-scale seesaw. You could have this term in red here. It's a small mass parameter here that comes from a term like that. This term, of course, violates lepton number. But this mu can be a small number. So you're violating the lepton number by a small amount. And this gives you the mass of the light neutrino. It gives you a term like this, proportional to mu and to md over mr squared. So from this point of view here, it has kind of like the same structure of the seesaw. However, it has also this mu, which is small. So the smallness of the neutrino mass is not due only to the large mr, but also to the smallness of nu inverse, which means that if you want to reproduce the neutrino masses, you're not so forced to put this mass all the way to gut scale or something. So it could be that this, the heavy neutrinos that are in the model can actually be found in experiments. And the smallness of this neutrino mass is actually due to another parameter which is small. That's why it's called inverse seesaw. A kind of silly name because the seesaw is that one is small because one's big. And now one is small because something is all small. And you call it inverse seesaw. But, well, that's the name. And then if you also include this other kind of term, which you cannot include, of course, a term like this before you break electroweak symmetry, because this is part of a doublet. But suppose that after you break electroweak symmetry, or you can put a Yukawa with another field or something. Yeah. This term here is called a term of a linear seesaw because it also has a small parameter here that appears here in the matrix in these non-diagonal terms. And they also create a small mass, but it's of the order of MD over R. So basically, it's linear in the Yukawa, while this one was quadratic in the Yukawa, so let's call it linear seesaw. And you can also put this one here, as Diogo was mentioning, but I will assume this is 0. So I will just remove this term because it won't do me any difference. Now, what?
These small couplings that they're introducing, can they be naturally small?
Well, you can argue that they're naturally small because they break a symmetry.
Number.
Right.
Yeah.
And so if you put them to 0, they are protected. They would stay 0 with the loop corrections. And if you put them to a small number, all the corrections will come proportional to them, so they're protected. Yeah? But the point is now you want to know, I mean, is there a way that they come from some dynamical thing? This is the idea of, yes? This one, yes, that's what I said. Yeah, this term is explicitly breaking SU2. You don't want that. So you can assume that this term appears only after you break electroweak symmetry.
So you could just put a Yukawa coupling there.
I can put a Yukawa coupling or something. Right, exactly. Yes, yes. Yeah, you could put some kind of term like that of this form where you, instead of this new R, you put the SR, and then when you break the symmetry, etc. Now, the other thing to notice here is that, well, you have one light neutrino and two heavy ones. And the two heavy ones, they have a mass of the order of the large M, plus or minus this mu inverse. The other one also contributes to splitting, but it's very, very, very small. So we can neglect that. So this guy is actually, this parameter is controlling the splitting of the two heavy fields. And that has some consequences for CP violation in leptogenesis. We'll see. When actually, if you have a Dirac field, you can always decompose a Dirac field in two Majoranas with the same mass. And if you have two Majoranas with different mass, you have two Majoranas with different mass. Now the question is, how is the limit? So if you get these guys closer and closer and closer in mass, you end up in a region where you call them, well, quasi-Dirac and pseudo-Dirac. I mean, there are two names. One is quasi-Dirac and the other is pseudo-Dirac, depending on the scale. Well, it doesn't matter. That kind of thing. So eventually they come, if they overlap exactly, well, you have a Dirac field again, and they separate. So how much do they separate? Well, the point is, if the separation of the masses is comparable to the decay rates, then you're having something that could be interesting. If they are separated more than that, then they're just two Majoranas. I will show that.
So at this point, they're not stable because they're not stable.
What?
They're not stable. They can decay. These guys.
The neutrinos? Well, yeah, sure. The heavy ones can decay because they have, you know, they have mixing with the say standard lepton sectors. You could have, for example, with the charge current, you could have a heavy neutrino going to an electron, and here you have a W. And this coupling here has some kind of a mixing parameter, you know, like a EN, just like a Kobayashi-Maskawa or something.
have any candidates for dark matter at this point.
What?
You don't have any candidates
Not
for
yet.
dark
No,
matter at
no.
this point.
Yeah.
Later.
No. Right. So next. So this proposal is now to have these, these breaking terms as a result of some dynamical process, through condensation. And well, first, let's see. Where am I here? Yeah, we want to reproduce this red term and the blue one. So this is the same as we had before. Now, this term here can be put, by hand because it conserves lepton number. But now you have these 4 fermion interactions. This is with only the S field, so this is something that could be mediated by some, scalar particle, singlet. While here you have this combination, which is the doublet with the singlet and singlet and doublet. And this will generate the linear term, the linear seesaw term, and this one the inverse. So I'm not going to go into describe how is this 4 fermion interaction caused. They must be mediated by something. Okay? Let's just simply assume that these 2 terms could be there at some underlying theory. And now, what happened below that? So if this interaction is strong enough, you could form some bound state here. And so the bound state in this case of this term will form a composite singlet scalar, singlet from the standard model, singlet scalar. And here, on the other hand, you could make a composite particle which is a doublet. And then later on, because of the strong interactions, if you have some kind of critical value on these couplings, you can have condensation. Condensation, from the point of view of the composite scalars that you form, means vacuum expectation values of the scalars.
Once you start adding these 4 fermion interactions, are they the most general thing you can add consistent with symmetries, or could there be more 4 fermion operators?
The ones I just put here are enough to reproduce the inverse seesaw and everything. At this point of level, I don't think you can put more than that.
To use that, I understand, but
Yes.
would the symmetries allow you to add more, right? Because you don't know what these higher forces are, so there could be other 4 fermion operators.
Yes. Yeah.
Vector, 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 vector.
Yes. Yes. You could. Yes.
You'd still the scalar probably figured
Right.
you could use.
Yes. Here I just assume this is like a.
There's some weird things you can do,
Yeah.
so I don't know.
Yeah. Yeah. Here the structure of the 4 fermion interaction is like a scalar kind of thing, right? It could be vectors like something else. Yeah. So the point is that after if you want to, to treat this as you think that this is a composite field, so in your Lagrangian you end up with something that has a Yukawa term. Basically, this field is this what is called bilinear term there that you have a Lagrangian like that. If you take the equations of motions of this, you reproduce the previous Lagrangian. And as you now run from the scale, let's call it lambda, down to a lower scale, let's call it m, you will also produce the dynamical kinetic terms for this scalar field. Here I just take an example of just one field like that. And so you have the running of these couplings below the scale. The condition of compositeness is that the Z the normalization exactly has to be 0 at the scale of compositeness, and so on and so on. And while the Yukawas have to be large because they are responsible for the strong interaction, etc. And so, well, we did the running of these couplings, and actually the sensitivity to the initial value is not so large, so you can fix this at any value you want, at the scale lambda. At the end, what you need to do is actually to have the theory at a lower scale. No? So, so when the field acquires a vacuum expectation value, the condensation, well, the field has, the VEV plus a scalar part plus an axial, pseudo-scalar part, if it's a singlet like that, or if you have a doublet, it will be like the Higgs, etc. So let me go to the frame here. These are the fields that I have. This is the standard model field, as you know. It generates this mass term. That is the Dirac kind of thing, we know, with a small mass m. Then you have the two composite scalars. This is a doublet, and this is a singlet, right? And this is the one that generates the linear seesaw term, and this one generates the inverse seesaw. And each one of them have their own VEV that we'll later on have to find out what the values have to be to fit the phenomenology. So you see here the mu linear seesaw is proportional to the VEV of this doublet, and the other one proportional to V phi. This is the effective Lagrangian when you are, at lower scales. So you have the standard model. This is also a standard model. And you have the extra kinetic term for the doublet, for the singlet, and an effective potential of the scalars. And these are all the Yukawas that you had before, plus this term that was originally in the Lagrangian. And you can build here the effective potential with all the possible combinations and parameters. All the quartic terms are with a coupling called lambda something, okay? And then the quadratic ones have this mu square. So to keep like the notation that you use in the standard model. And there is an extra term here that mixes these two guys, or three fields, which is kappa. That you cannot avoid. I mean, you need that. All right? Yes.
Can you go back? So the sigma is SL. I don't understand why the S will condensate with the left one. Because the left hand is not charged under this. You assume a kind of new strong force, right?
Yes, there's a strong force that. Yes. Let me see here.
So yeah, the sigma.
Yeah, the sigma. You're forming. Yeah, you're assuming that you're forming a condensate with the with the lepton doublet. Yes. Well, basically,
No, it has a four-prime interaction.
it has a yeah.
Go back.
Yeah, exactly. It has further back. Come on. There.
No, but okay, that's fine. So it's a critical couple.
So you're assuming that there's some, some kind of strong interaction of between these fermions. So your concern is, could that interaction cause problems in the standard model at lower energies as well?
I can understand you can generate this kind of interaction from a
Yes.
higher scale, but if the S is also strongly interacting, then it would also condensate just like LL.
Yeah, I don't know. It's a good question. I don't know. Well, he's concerned that he's concerned that we can ruin the standard model because you could have condensations of the doublets of the light, LL. In this frame, here I'm condensating the SS and here the LS. So, but the question is, if it's a strong interaction to condense the LS, could it be also something that condenses the LL? We certainly we don't want that. So, something to explore it. It's very slow. I don't know what's happening. Anyway, so we were here, right? Yes. So when you have, of course, just a typical Higgs mechanism, when you have the wave, you also create a mass for the fermions and so forth and so on. Okay? So that's what happened here too. And now you have so many parameters here that you can possibly think that you can predict anything. But actually, it's not true. This is very restricted. Because many of these parameters just appear, as a result of this compositeness, and they run to some values, so they're kind of fixed. So here in black are the ones that are free. Yeah, I put them here. So this is the MR. This is the mass that was initially in the theory. These are the two waves of the extra fields, and this is the Yukawa that gives the Dirac mass to the neutrino. Those are the free parameters, which actually this one and that one are the ones you already have in the typical original Seesaw, but now it gets richer. Now these Yukawas, of course, appear because of the non-perturbative origin of the interactions that causes the condensation. All these scalar couplings have to go to 0 at the condensation scale because this is how the composite scale. This is how it appears, and then when you go to lower energies to reproduce the phenomenology, you need some kind of hierarchy. So these couplings are of the order 1. This is like a 1/10, 100th, and 1 in 10,000. And this coupling kappa is very important to keep, and it's a rather large number also. So let me see what results in this. You end up with a scalar spectrum that has the would-be Goldstone bosons that will be absorbed by the W and Z, which are mainly the standard model Higgs. Then you have one standard model Higgs boson. You should have that. Which the mass of this guy is proportional to the wave of the standard Higgs boson. Then you have some pair of charged ones, an extra heavy scalar, and a pseudoscalar. And all these have to be heavy so that you're consistent with phenomenology, heavier than, 600 GeV or something. So that forces some of the couplings. And then you end up with something that if you do that, you will not be able to make other two scalars that are in the theory. You will not be able to make them heavy. So the only thing you can do is try to make them sterile. And there is the one massless particle, which is the majoron. It's like the Goldstone boson of the lepton number breaking. And another field that is not massless, but it's very light. And this could be a candidate for dark matter, depending on where it appears in the cosmology. It could be a warm dark matter or something. It cannot be the only dark matter particle if we want to fit, all the cosmology, but at least it's consistent.
Why does that one have to be light?
If you impose that the other ones are heavy, you always get one that is light. You fit the parameters. There's no way you make them all heavy. So the model is rather constrained, actually.
And that is stable under radiative corrections because it's a scalar.
And yes. So,
Claudio, what do you call light?
in this case, it's like 100 keV or something like that, masses like that.
Okay, so much beyond the
Yes. below MeV or something. Yeah. So here, did I put it right here? Yeah, so you need, well, you see this ratio of these two. This is the singlet, and this is the doublet VEVs. And you need this ratio. In some cases, you can make it very small or very large. In some cases, very large. So consistently, it's better to make them very large. So if you make this ratio very large, you end up pushing the masses of all these extra scalars, or most of them, to large values. And also, you push, it's lucky, the massless majoron, it becomes sterile because it becomes mainly one of the components of the pseudoscalars. So, and this is done precisely by this imposition, which is same as that. But this guy doesn't become heavy, so you have to impose, well, this condition and some other ones, which is like these two VEVs have to be much more than the standard VEV, and in addition, some couplings, quartic couplings, to make them relatively sterile to the standard model particles. Well, if the mass is, as I said, like 100 keV or something, the main decay of the S0 is into neutrinos, essentially. So you have to make sure that that doesn't, make them decay all the time before the universe, present universe, if you're going to have it as a dark matter. So this is a spectrum, basically. Where is the... Yeah, so you see, this is the light scalar. It comes to lambda phi to V phi, and this VEV has to be very small compared to the standard, so this will be lighter, much lighter than the Higgs, essentially. So these are runnings here, is not relevant. Then also we have to impose that the large scale, lambda, should not be much larger than 100 TeV or so, because if you do that in the running of the scalar potential, you end up with instabilities. So we fix lambda to just 100 TeV and calculate everything else. Well, this is the normal VEV to reproduce the Higgs of 125 GeV. And this is much smaller, so you can neglect that. Let me see. Oh, sorry, let me go back here. There's something else. I fixed this to 100 TeV. MR, we want it to be below 100 TeV, but for obvious reasons. We want this mass term to be existing in the theory below the lambda scale. Otherwise, it will be integrated out, and you have no neutrinos, no heavy neutrinos. And now, for leptogenesis, you need you need lepton number violation, which you already have. You need CP violation so that the rates of processes in one direction and the other are different, at least during the time when they come out of equilibrium. And you need some condition for out of equilibrium. So, well, the condition out of equilibrium is that you need at some point the rate to be less than the expansion rate of the universe. Okay? This can be done. And the CP violation part is a bit trickier. For CP violation, well, in this model, we use only one generation of, one family of leptons, so there is no CP phases. Yeah? So it won't work. But if you have three families, then you will have complex phases, and then it's fine. But you need more than that, because to have CP violation processes, you need to have interference of amplitudes with different CP phases. In addition, the amplitudes have to have a different absorptive phase. Otherwise, when you square the whole thing, the two rates become the same. So where do you get an absorptive phase in this case? From this condition, the quasi-Dirac condition. If delta M is close to gamma, it means that you have two amplitudes. One of them, say, mediated by the neutrino in the intermediate state. The two amplitudes if the neutrinos have masses very different, there's no way that kinematically you will have the same final state resonant at both neutrinos. See what I mean? So you have some kind of process here, and you have this neutrino here, and then something else. And then you have two amplitudes. If M1 and M2, if the masses are different, there's no way you will have the same kinematics here, where both are resonant. So only one of them dominates. Unless the masses are close enough within the range of gamma. So that's the condition that you have to impose to have CP violation. Some people call it resonant enhancement of CP violation, but actually, well, it's a name. So it means that these two peaks must overlap in some finite region. And this can be done because, as I show you in the model, the splitting of the two heavy fields is rather small. Well, you have to make it precisely to this range. I mean, because even if the small, they could still be far apart. So you have to adjust it. But it can be done. So, well, these are the numbers that you have to put in to fit that. And basically, that's all the fitting of the numbers that we got to have this. The MR, we put it in 10 TeV. The lambda scale, as I said, it was 100 TeV. You find the Yukawa couplings, the VEVs, etc. And you can reproduce what we were imposing. Now, the observable predictions of this is, of course, that you have, as I said, a dark matter candidate that you have to make sure that lives long enough. The decay mode is into neutrinos, so you have to adjust the couplings here to make it live long enough, or it will disappear. Then the neutrino mass, in this case, with one generation, actually appears to be extremely small. So this is not contradictory, because one of the neutrinos could be even massless. But if you have 3 generations, you will have to adjust things so that not all of them are so extremely small, of course. And then you also have a problematic thing here that the Z could decay into these extra particles, so you have to make sure that this is suppressed. And yeah, it also can be done. I mean, you find the branching ratios like 10 to the minus 21, to most like that. So it's safe. And now the origin of the...
Sorry, if you go back, there's S
Yes.
to 2 photons. So this is a one loop process?
Yes, I think it is, yes. This one here, yeah. Yeah. And this eta is the majoron, yes. And since the majoron is massless, you can also have, decays of the heavy, the light neutrinos can go into the lightest of them, etc.
And S does not couple to quarks, only to leptons.
S, yes.
What about the effective number of relativistic?
Sorry?
Effective number of relativistic neutrinos. Or in general?
We didn't do the cosmology of the stuff, no. So there's something probably could be done. Maybe you can rule it out completely then, I don't know. And so the final words of this, compositeness, you have to have a coupling that is critical. This is a standard thing that, what's the name? Muggiano-Lasinio, and then Bardeen, Lindner, and Hill, I think. Chris Hill, I think, right? Yes. Yeah. So now you can have, it's a speculation, you can have the inverse seesaw, basically the singlet part as the fundamental, and this could induce the linear seesaw. And this could be even subcritical, so you don't have the condensation of that sector, which is okay. Or the other way around. You can have, what is this? No, forget it. You can have the other way around. You can have the linear seesaw is a fundamental one, you see? And then this induces the inverse seesaw, et cetera, et cetera. So in that case, well, you will have slightly different parameters, but it also can be adjusted. But this is something we don't have a handle on that. This is, it's further things. So these are the conclusions. Essentially, even when it looks like you have lots of parameters, etc., the model is very restricted, and it's quite easy to rule out if things go wrong here. You predict, of course, some heavy neutrinos that could create leptogenesis. You have a majoron, which is a massless scalar. You have another scalar, which could be a candidate for dark matter. And all these are restricted to very small range of parameters, so things can be tested. And in addition, to get the CP violation for leptogenesis, you have to include the three families. So this is something that's not done here. It's only kind of like a toy part of things. And when you put the three families, maybe things get much more complicated. Who knows? So that's it. So the last words I want to say is that, well, one of my friends and collaborators, Eduardo Pontón, is the one who actually invited me to come to this workshop, and he sadly passed away. So, and I understand that you organize a workshop for Memorial and on 28 or something like that. And unfortunately, I won't be able to be here. I knew this too late also. So I just wanted to mention to him as a good friend of mine. I came many times here, and he was a wonderful host. He took me to different places also. This is actually a picture of the Sala San Paulo. We went to see a concert. And there we were with Rogerio, with this singer that we went to see the other day, Seumar. This picture is from 10 years ago or something. No, not so much. It was from 2015. Yeah. Okay, so thank you.
Thank you, Claudio.
Yes. We didn't do that, yes. This is true. That is something that all the cosmological part we didn't really analyze, but this is something that we have to check, yes.
Probably you require that the lifetime of this particle is larger than
You have
the
to,
universe.
yes, you have to do things like that, and to make sure from the point of view of the, well, some things we checked, and they work okay. I mean, you can make the lifetime long enough, longer than the scale of expansion. But there are still some channels we have to make sure that are under control.
Even a majoron could contribute to the relativistic degrees of freedom.
Right. Mm-hmm.
It's less than a neutrino, but it can.
Right.
Can it be considered as a model with some extra hits doublet without to avoid what about condensate? So just consider it as a normal extension of
To you mean to consider the standard Higgs as a
standard hits plus you have another hits doublet.
At low energies, that's exactly what you're saying. At low
Yeah,
energies,
yeah,
you
yeah.
have a Lagrangian that
Yeah.
looks like an extension of the
Yes,
standard
but
model.
we can consider it in full high energies too. Why not?
These are normalizable. Yeah, that's what you're saying, right?
But it's normalizable or not? I mean, it's not normalizable.
I think it is. At low energies,
so
yes.
If it's normalizable at low energy, it will be normalizable.
Yeah.
Any energy.
Okay. Can I?
Sure, go ahead.
My
Yeah.
feeling about this is that yes, you can do this thing and just have an extension of the standard model.
Yes,
You don't have to think about the what's happening at high energy.
Right.
Now, in this model that Claudio is developing, there's some there are relations between the coupling constants that have to be obeyed. So you reduce the number of free parameters because you have relations that arise because of the condensation feature or the
Well, we want to attach these things to the neutrino matrix, basically, right? So you have this new inverse and new linear to be of some size to reproduce the neutrino masses, etc.
So for special parameter, it will be the same as you.
Right.
Yeah. So you can show the Lagrangian again, right? Because that's it's an effect Lagrangian. I think they're normalizable. Like a
It's a two doublet plus one singlet, actually. It's a two doublet plus a singlet. Why go so slow this thing?
Make sure Prisma, you can implement this this afternoon. You can implement this in micromegas.
So this is it's a two doublet plus a singlet, right? Yes.
But not with this cap.
That's the right-handed neutrino, yes. Yes.
Not
Well, they have to do Kawa first. Yes. Sure.
So that's what you have to do.
Yeah. Exactly.
It's good exercise for this afternoon. Yeah, but I think the issue is this, that you have relations between these couples, so they're not all free parameters, as Claudio said.
Yes, but that's because you have a particular structure of the four fermion threads, right? If there are more four fermion couplings, then you would have less constraints on the
Right.
model.
Yes.
So this is why that goes back to my
Yes.
question, whether you could have more
Yes.
four fermion couplings.
Yes. That's true.
Your estimation for the decay rate of the matter candidate was in electron volts, something like that? No. Your estimation for the decay rate.
The decay rates was let's see. But I don't know why this goes so slow here. I think I did something wrong with my transparency, the animation or something. No, it's not here. You wanted no. Oh, yes. This?
How much is that in seconds? Do you know?
This? Oh, no. Well, let's see. Well, you have to make me calculate here. Yes. But well, there was an issue though. I don't quite remember the issue, but you actually this is a condition for the particle to be stable in the age of the universe. But actually, you needed to impose an even smaller value here. I mean, a slower rate, probably like at 2 orders of magnitude or so. So it would be like 10 to the minus.
Suppression, by the way. From where came that suppression?
We don't know. I mean, you needed to have it, but when you calculate this thing, it gives you like 10 to the minus 32 or something. So you're kind of in a tense situation there. Well, you can estimate. Let's see, MS was like 100 keV or something, and then.
So he just adjusted Yukawa. Put in by hand. Right? Is Yukawa is by hand.
Right. Yeah.
You need to put that Yukawa.
So let's see. What was it like? It was so you have like 10 to the minus 36 that comes from the Yukawa, right? And the MS was like 100 keV, which is 10 to the 5 eV. So that gives you 10 to the minus 31 divided by 8 is like a 10 to the minus 32. So you are kind of, tense with this requirement of less than 10 to the minus.
But you can reduce the Yukawa.
But you can reduce the Yukawas, and yeah. So.
Yukawa is an outcome of your model. The model predicts
S.
Is the S from the SS?
S is a combination. Well, I'm going to take a year if I go back there. You have you have the Higgs, right? The Higgs that has some kind of charge thing here, and then you have the neutrals, which is, well, you have the Vev plus the Higgs plus some A. Then you have the other doublet, which has a Vev here, I think. Then plus another scalar. Well, I don't know what you call it. And here also some charge fields that combine with that. And because these and the other ones here, they combine into the extra charge and the pseudo-Goldstone bosons. And then you have the singlet. Mm-hmm. In the singlet, you have also a Vev, you have a scalar, and you have an axial. So what's the question again? The S? The S is a combination. It's a combination of essentially these three fields. This one, and that one. One combination, of course, is essentially purely Higgs, the standard Higgs. Then you have another one that is very heavy. And the majoron comes from the axial. And then the other one is the light one. That's it.
Probably also be suppressed to the neutrino, right? Because it has the same kind of seesaw mechanism.
It should be suppressed to the coupling of the neutrinos, yes. Mm-hmm. Yes, but, well, to put there the couplings to the fermions, et cetera, et cetera. But it's not the Dukawa, it's in addition the mixing also is in between. Yeah.
So I have a question about the 100 TeV scale that you said.
Yes, yeah.
So you said that came from vacuum instability.
Right.
So,
when you put the loops.
So usually the vacuum stability is some quartic going negative.
Right. Exactly. Yes. Yes. Yeah.
There are different quartics there.
Yes.
So you analyzed all of them, and this is the minimum one?
We actually analyzed, I don't know if we analyzed all of them, honestly, but we checked the ones that are, the ones that are not mixed, the ones that are like the dominant. H to the fourth, phi to the fourth, and sigma to the fourth. We try to guarantee that these guys don't go negative.
The 100 TeV scale, that's one of
That's kind of like, yes. If you go above that, you're risking to have negative when you fit the values at low energies. Mm-hmm. Yeah.
Some more questions from Claudio? If you go above that, this is an effective theory, right? So
Yes.
I'm a bit confused.
Right. So you want.
Above that scale of theories that are different, so I'm not sure that.
Well, you don't. I mean, let's see. You want the effective theory to be valued from lambda down there, right? And if you're here, your parameters, you run up here with your effective theory. You don't want your effective theory to become unstable before you reach the. That's kind of the idea.
About the CP violation.
Yes. Yes. Yeah.
So is that correct that the phase comes? Can this phase, the complex phase come from the off diagonal width? It comes completely from the width, or you have to have a explicit phase?
You have to have complex couplings that come from whatever theory you have.
Isn't it possible to have some effect from the off diagonal width? Because that's
Let's see.
you have one loop, so it's like the width is like a loop.
Yes. Yes.
So if you have a neutrino, so you have on your CK, on mixing matrix, you have some imaginary parts from that loop.
Yes.
Would that be, can it generate also from that?
Well, this thing essentially adds up to having, right, you have, well, something like that, right? This gamma here had to do with that. Huh? well, you have an I somewhere, which gives you an absorptive part of the propagator. And so you need the two neutrinos, so should have propagators that are not exactly the same. So when you have interference, you have this phase going around there. It's an absorptive phase that is not conjugated when you take the conjugate process. And in addition to that, you need, of course, the, let's say, Kobayashi-Maskawa kind of phases of the parameters. You cannot have only that. You need, of course, also the Kobayashi-Maskawa kind of couplings, of course. Yes. You need to have, say, so you have one amplitude.
Would that also be a source of off-diagonal width? Would also that be a source of CP variation or not?
What do you mean by off-diagonal width? I'm confused.
For instance, if you have the mask mixing, right? You can include the widths in the mask.
Yeah.
It's a loop effect, and it usually is not important at far from the pole because you don't get any effect. But now if you have also if they are near degenerate, you can have some effect of the off-diagonal part. So you have imaginary parts from the off-diagonal. So for instance, S.
Yeah, of diagonal, you mean that this is, say, neutrino 1 and this is neutrino 2, something?
Yes.
Yeah.
This kind of thing.
Yeah, I mean, of course you have this kind of thing, but you can parameterize it the way you want. You can re-diagonalize everything. And
You're always working with eigenstates.
yes, you can re-diagonalize everything, and it's still the same. The point, when you want, CP violation means that you have a process that occurs at a different rate for one process than the conjugate, right? That's essentially the thing that you need. And if you have, say, you have an amplitude for a process, then the rate is proportional to the amplitude squared. And if that's the only thing you have, the CP conjugate process is that. So it gives you the same rate. So you don't have CP violation. So you need a kind of interference between two amplitudes at least. So you have two amplitudes, one amplitude plus the other. And now you have the rate. But now you do the complex conjugate process. I mean, the charge conjugate process. And that guy has a rate like that. Which again, when you do the square of that, it gives you the same rate again. So the only way you have some surviving interference term that doesn't cancel is that there must be some extra phase, e to the delta, that you're not conjugating here, which is the absorptive part, the difference in absorptive part. But again, if you only have an absorptive part, you don't get CP violation either, right? You will have A1 plus A2 e to the I delta, and the other process will be just the same. So you need to have both things. You need to have some parameters that are complex in your Lagrangian. In addition, you have to have a process in which you have the beating of two amplitudes with the different absorptive parts. In K decays, for example, the absorptive part you get because you have K long and K short, which are different, etc.
It's always the absorptive part is always.
In K decays, you have the part that you have two K long, K short, or K0 bar, and they have different decay rates and everything. Or in B decays, well, the same. So in this case, you have, well, also the same, because this is also it's a loop that is showing you that you have different decays. Right?
Okay, further questions for Claudio? Now let's thank Claudio again. You can go for lunch there. Or stop by your office. You woke up at 3 in the morning, must be.